Hello, everyone. Our workshop will start at 7 p.m. Hi, everyone. For those people who just joined this meeting, we will start our workshop 2 minutes later. Hi, everyone. It's 7 p.m. now, so I will start my workshop on time. Okay. So now I had shared my screen so you can see my presentation slides. Good evening. My name is Hui Wen. I'm an undergraduate student from Electrical and Electronic Engineering. I'm from Machine Learning and Data Analytics Club, the academic department. I'm very glad to have the chance to share with you the topic of AI security. Today, I'm going to make a workshop on introduction to adversarial attack on machine learning model. I believe for most of you, the terminology adversarial attack is a little bit unfamiliar. Because in our mind, machine learning and artificial intelligence are mostly used for good purposes. They bring benefits and convenience to our day-to-day life. For example, have you used the commute estimation function in Google Maps? Users can set a starting and ending point, and the model will calculate the estimated time needed to reach your destination automatically. So it saves a lot of effort for you to search for map and calculate the time you will need. Another example is that the weather forecasting model. By inputting history weather data and other possible factors, the ML model could predict whether Oh, sorry, can I check with you that, can you hear my voice? Okay, sure. Sorry, because just now my microphone cannot work. Okay, thank you. Another example is that the weather forecasting model. By inputting history, weather data, and other possible factors, the ML model could predict weather in a week, even in a month, at a very high accuracy. So it could achieve above 90% and even 99%. So this performance is far beyond the one that humans could achieve manually. However, have you thought about that? Machine learning could be used for malicious purposes. In our mind, they are used for good purposes, but actually they can cause adverse effect on other models. A machine learning model could attack and fool other machine learning or AI systems. Today, I will give you an overview on AI security with a special focus on adversarial attack and defenses techniques. Then I will talk about the Adversarial Robustness Toolbox. It's a very popular Python library on AI security among researchers. So this page shows the outline of today's topic. At first, I will guide you through the background of AI security, why we need to put attention in such field. And secondly, let's go through the development history so that you can have a better understanding of adversarial attack. And then we will dive into the definition of adversarial machine learning. And after that, categories and some typical AI security attack will be introduced. Lastly, I will bring to you a very useful toolbox with which you can implement various digital attack and defense techniques on your own. So after this workshop, you are expected to have a good understanding of AI security, attack techniques, as well as how to use Adversarial Robustness Toolbox. Now let's move to the background of AI security. Machine learning and artificial intelligence are widely used in our day-to-day life. It has a lot of applications, especially in security systems. For example, AI has been extensively used in environmental perception module in autonomous car. Do you know Tesla is a large electrical car manufacturer? Do you know Tesla's autopilot is based on machine learning algorithm? So the mechanics is like this. The input data are the raw video streams from 8 cameras around the vehicles. And then the footage are processed through convolutional neural networks to conduct tasks like object detection. And then it can identify surrounding environments. If the data of surrounding objects could be detected, for example, those pedestrians or traffic signs or road line, etc. those information will be sent back to the central processing systems of the autonomous car and to make intelligent decisions and without any human effort. Besides this example, some of the surveillance systems use face recognition algorithm. Such system uses biometrics to map facial features from a photography or video. It compares the information with a database of known faces to find a match. It can help to verify a person's identity in a very fast and accurate manner, and it's without any human effort. Similarly, door access system with voice recognition are also very common in real-life application. The mechanics are very similar to the facial recognition system, except the input data is audio. However, with increasing application, the security becomes a big problem. So you can imagine, what if a hacker could distort object detection model in a self-driving car and make it misclassify a pedestrian as a road line? Such attack will cause huge financial loss and even physical injury. Thus, security is a very crucial topic with the development of machine learning and artificial intelligence in our daily uses. Now let's take a look at the development history of adversarial attack. In 2004, attack on linear classifier of email spam was proposed. In such filtering mechanics, emails contain keywords like free, giveaway, or discount will be classified as spam. However, the spam could be undetectable by simply not using these words. So that's the initial point of adversarial attack. So that's quite simple and easy to understand. In 2006, a research called Can Machine Learning Be Secure? Proposed general classification of attack. It discussed the possibility of fooling machine learning model and decreasing model performance. So at that time, the field of adversarial attack was taking shape. In recent years, we start to use a very complicated models. It's a family of models called nonlinear classifiers. They are dominant in performing classification or regression tasks. It contains it contains hundreds, even thousands of parameters and weights. Thus, it could provide a very accurate result compared to those simple linear classifiers. And today, adversarial attack on those complicated non-linear classifiers like SVM and neural network are also proposed. As you can see, the image from left to right, it shows the evolution of the adversarial attack from very simple spam to complicated neural networks. Now let's move to the definition of adversarial machine learning. Instead of doing something good, adversarial machine learning is a machine learning method to cause malfunction of machine learning and artificial intelligence model. The images okay. Sorry, it seems that someone muted me. Okay, now let's continue. The reason we are instead of doing something good, adversarial machine learning is a method that can cause malfunction of ML AI models. The image with green background gives a simplified structure of adversarial machine learning from training data set to training model stage to test and finally generate raw output. So adversarial attack can take place in those stages. However, what's the reason that we are able to attack those ML models? The reason is that the lack of explainability. According to the degree of explainability, ML model could be divided into two categories, the white box and the black box. The white box indicates simple model with easy to understand structures and a limited number of parameters. For example, the linear regression or decision trees. They are examples of those simple models. In contrast, complex models such as deep neural networks with thousands or even millions of parameters are considered black box. This is because the model's behavior cannot be comprehended easily when we are not able to access its structure and weights. Hence, adversarial attack will be more effective in such black box attack. It's because of its complexity and hard of interpretation of its internal mechanism. So furthermore, adversarial attacks, they are categorized into different types. In the following sessions, I will introduce definitions and some examples of 4 categories of adversarial attacks. Now let's take a look at the evasion attack. Such attack as small digital perturbations to model input to interfere model inference. The input with perturbation is called adversarial examples. As shown in the first image, the perturbation is a sign of the gradient of targeted machine learning models cost function J with respect to the input image X, and then we times a constant 0.07. It seems like this formula is quite complicated, but actually it's not. It's simply the sign of the gradient. So as we can see, this constant 0.07 decides the portion of the noise. If it's larger, there will be more noise added to the final image. If it is smaller, there will be less perturbation. And it's very intuitive that with larger constant, the attack performance will be better. However, it will become more detectable to human eyes. So as you can see, originally X, the input image, is a panda. The confidence is 57.7 confidence. After we add the noise generated by this formula, it becomes another totally different class. And the confidence even increases to 99.7. So that's significant change simply because such noise. And this attack is called fast gradient sign methods. So that's the most important evasion attack. And that's the starting point of evasion attack. So at the end of this workshop, I will show you a notebook that how can we implement this attack, use ART, use the Adversarial Robustness Toolbox. Evasion attack can be implemented physically. So previously we discussed the digital attack. The evasion attack can also be used in physical world. So it's quite practical in real world application. For example, as shown in the second image, a stop traffic sign could be misclassified as zero bottles by adding adversarial patch. You can see the patch is here and here. So originally it should be the bounding box of a traffic sign. but now it changes to serial bounding box with label bottle. So that's the power of adversarial patch. But how can we generate such patch and ensure that the patch has attack power and is able to fall detected? We can do so by optimizing attack performance in digital world. If we have targeted model information, so we can call it white box attack. We can optimize it iteratively by increasing cost function of a targeted model, because our ultimate goal is to cause model generating wrong results. So compared to the training stage, we want to decrease the cost function as much as possible because we want to improve the accuracy of the classification results. However, in this stage, we want to cause the model to generate wrong output. So we increase the cost function instead. And also, if the size of the patch is small enough, such evasion attack will be extremely dangerous because it's not visible to humans' eyes. And if the object detection model of autonomous car is flawed, so we can imagine how much financial or physical loss it will cause. However, sometimes we don't know the parameters or training data of targeted model because it may be protected. It might be the properties of some company. So attacker can train evasion attack on a very similar model and transfer the attack to the targeted one. So this process has a metric called transferability. It measures how well the attack can be transformed from the one we know, the white box model, to the one we don't know, but it's the target, the black box system. So this transferability measures the generalizability of the attack. Now let's move to the second type of attack, poisoning attack. Different from the previous one, we modify input data. Such attack modifies training data to attack model during retraining stage. I have an example to show you. For most of the AI model on cloud, they constantly collect new samples to retrain model, such that it could adapt itself to the new situation. For example, the recommendation system of Netflix will collect users' preference according to which contents they click or which movie they had watched recently. Then it will retrain the model to improve recommendation accuracy. So such retraining stage will happen from time to time to improve the model itself. If the attacker can inject crafted samples to contaminate the retraining data, the model performance will hence be adversely affected. In research, Jack Elsky et al. Found that mixing a small number of adversarial examples with training samples can significantly affect the accuracy of AI models. In dosage recommendation system, by adding 8% of malicious training data, attackers can cause a 75% change of the dosage suggested by models for half of the patients. So from these examples, you can show the power of poisoning attack with a very small portion of contaminated data. Actually, we can change the results from a very large degree. And another example is that there was a team of hackers. They successfully distorted Google spam filter by sending some malicious emails. So you can also see the attack power of the poisoning attack, because even a small team of hackers, they can win against a tech giant like Google. So this image at the right-hand side shows the simple structure of such attack. We add malicious training data, mix it with the normal training data and send it to model, and finally it will generate wrong results. Now let's move to the third types of attack, backdoor attack. It modifies model structure during model implementation. Backdoor attack in neural network can be achieved by adding crafted neurons, and then the model triggered by the specific input that is only known by attacker. So it's very intuitive that such attack is more effective in neural networks because of large numbers of neurons and parameters. So for most of the neural networks, there will be hundreds or even thousands of parameters and neurons. So it's hard for people to find out which one is malicious. So those crafted neurons, they hidden very well among other common neurons. So it's hard to detect such attack. And I show you an example from a research. Wenger et al. Proposed digital and physical triggers in facial recognition models. As you can see from the left-hand side, this is a digital trigger. There is a small square patch on this person's face. And the right-hand side is a physical trigger. They use some dots, sunglasses, tattoo, and some tips as a way to trigger the backdoor. You can see that actually this attack is very practical. It's hard to detect because attackers with glasses and tattoo may not be considered suspicious. Thus, it has large potentials in attacking identity verification system. Now let's move to the last attack, the model extraction. Such attack will steal model information by analyzing the input, output, and other external information of a system. Parameters or training data of the model could be speculated. For example, we can do that by keep sending requests to the machine learning model and analyzing the output. The model information could be estimated according to large amount of data. Furthermore, attackers can craft adversarial examples using extracted models. So after we steal the information, we can use it to generate adversarial examples, like the evasion attack, to attack the targeted model. So that's really powerful and may cause huge damage to the targeted model. However, it may consider illegal to steal model information due to intellectual property. You can think that a company may spend several years and millions of dollars on implementing a machine learning model. So it's a large property to the company because they spent so much time and money, efforts on that. And the second reason is that the black box attack increases complexity and the difficulty of attack to a very large degree. In real world, the model of online services provided by tech giants like Big ML and Amazon machine learning have been stolen in the past. Hence, the model extraction attack could be really powerful in some scenarios. Here is a summary on AI adversarial attacks. So it's actually from an attacker point of view. We can attack the machine learning model here by poisoning attack to contaminate the training data. And then we can also extract the model information and steal it from the output. Besides the extraction, we can modify and add small perturbations or noise to input of machine learning model and attack it using evasion attack. Lastly, we can change the model's inference by sending some crafted neurons in this structure. So it will behave as we can expect. So here are the 4 evasions, 4 attacks. Now let's do a small quiz. There are 5 questions and it's on Zoom poll. So I will send you the question now, so to test your understanding of previous content. So now I have sent out the first question. Please choose the answer. Okay, I saw most of the people choose poison attack. Now I'm going to end this question. Actually, most of you got it wrong. It's evasion attack that modifies model input and creates adversarial examples. So let's go back and have a look. So its evasion attack modifies model input. Here are 2 examples. We can modify input by add perturbations like this, generate by the sign of the gradient of cost function. And we can also modify it by adding some adversarial patch. So what's the difference between evasion attack and poison attack? So poisoning attack actually modifies training data. So it sends malicious samples to contaminate the training data set. So there is a little bit of difference. And also it's evasion attack that creates adversarial examples, not poisoning attack. So there might be some difference between these 2. The main difference is that this attack is conducted in inference stage. So in this stage, the model will not be trained, and it starts to make inference when you send input data. So it's on inference. However, for this poisoning attack, so it's actually conducted in retraining stage. So it's not inference. So that's the main difference between poisoning attack and evasion attack. Now I believe most of you have know the answer of the first question. Let's do the second one. So this one is about fast gradient sign method. So my question is, what is the formula of the perturbation? Okay, now I'm going to end this question. Yeah, congratulations. Most of you got the right answers. So the formula of perturbation is constant times sine of the gradient of targeted model's cost function with respective to the input data. Okay, now let's take a look at the third question. For this question, most of you got it correct. The answer is backdoor attack. The keyword is that there is a specific input. So do you remember the backdoor attack? You can remember this by these examples. When there is specific input, for example, there is a person with dot on its face or there is a sunglasses, the model will behave abnormally. So it is triggered by a specific input. But for poisoning attack, we contaminate the training data set. So there is no specific input. We add malicious samples to the data set instead of a single input. So the answer for this question is a backdoor attack. So it seems that you have very good understanding for backdoor attack. Now let's do question 4. So which attack is used in training stage? Most of you got this question correct. There are 72% people answer it correctly. So that's here. So it's poisoning attack conducted in the training stage. We modify the training data. So what's the difference between poisoning attack and model extraction? So model extraction is not in the training stage. It's that we repetitively request the ascending request to the machine learning model, and then it will generate a lot of outputs. And then we analyze the outputs and try to figure out the training data and parameters of the model. And then we steal this model because now we know all the information of it. So actually it's not in the training stage, it's in the inference stage. It's the same as evasion attack, but it steals the models instead of modifies the input data. So here's is the last question, question 5. The adversarial attack is more effective on which model in the following? So it has multiple answers. You can choose more than one options. Okay, congratulations. Most of you got it correct. The answers are black box model and neural networks. But actually there is a little bit confusing because neural networks are actually a subset of black box models. So I want you guys to have a better understanding. So I put two options. So black box models means models with many parameters and weights. So it's hard to explain the internal mechanics. And the behavior is quite complicated. And for black box models, we generally refer to the nonlinear one, like the neural networks and the SVM. So that's why we choose these two answers. But for wet box model, it's a little bit too simple. So the adversarial attack cannot have good attack performance on that because it's easy to understand and easy to find those attacks. So that's why we choose black box model and neural networks. Okay, thank you for participating in this quizzes. It seems that you all have very good understanding of adversarial attack. Just now we talk about attack, but how about the defense side? In this part, I will briefly talk about the defense techniques that we may use to go against those attacks and make our model and architecture more robust. But now I will explain a little bit more on this figure. The right-hand side shows the architecture of an AI business model in real life. In real application, AI model runs on cloud, just like the Netflix recommendation system I mentioned before. It will collect data online and retrain itself to adapt to changes in users' behaviors or environment. Then the AI inference output by model will be sent to business deployment part, this part. That's where the data comes to use. In Netflix example, it could be the situation that the recommended TV series are displayed in user's main page. The defenses are at 3 levels. The left-hand side, the AI security column. So the first level is attack mitigation. It is targeted at preventing attack of a specific category. For example, we can mitigate those 4 types of attack: evasion, poisoning, backdoor, and stealing, which is model extraction. And the second level is the model security level. So we can make the model on cloud more secure from input data to model training stage and then to the output. So we want to have explainable data and make model verification so that this model cannot be accessed or queried by anyone, only if they have a valid identity. The third one is model robustness. And the last one is explainable model. That means we want to avoid black box as much as possible. We want our model to be able to easily be understood and have simple structures such that our model can become a white box. So that's most desired situation. The third level is a secure architecture. So this whole part, the AI training on cloud plus AI business deployment means AI architecture. So this one means we want to make the whole architecture of the AI model and the business deployment more robust. We can do isolation detection, redundancy, and other methods. So there are 3 levels of defenses that we can do to make it more robust. In this page, I show the attack mitigations which was discussed in the first level. For example, if I want to mitigate poisoning attack during model training stage, I can use ensemble analysis. So this row shows the different stages, and this part shows the specific attack that I want to mitigate. Now let's go into take a look at the final part, the Adversarial Robustness Toolbox. In this part, we are going to have some hands-on coding and take a look at the toolbox, how we are going to use it. It's a Python library developed by IBM for machine learning security. It's really useful because it supports all learning frameworks like TensorFlow, Keras, PyTorch, and MXNet, etc. It also supports all tasks like classification, object detection, etc. Besides the framework and task, it also supports data at all formats like images, tables, and audios and videos. Now let's take a look at the main website. So now I believe you can see the main website of this toolbox. It's simply an introduction, so it's not so important. It also introduced some features, but what's the most important is this part, the documentation part. So it's like a very comprehensive guide of using this toolbox. So there are several modules, you can click them. And then you will see the full list of functions in this module. And you can search docs, click this searching bar and type the modules that you want to use or you want to take a look. So that's a very useful website. Now we take a look at the GitHub page. So this page contains most of the important information of this toolbox. It includes the summary of what it can do, the defense and attack side, and also very important tables. At Get Started column, you can see some installations process, examples, and notebooks. And in the documentation, you can click them for a specific modules and how to use them. So that's the image in the GitHub. So it shows the perspective as an attacker. You can contaminate training data. You can extract the model, steal the model from the output information. And you can also use evasion attack by adding perturbation in the input data. And then lastly, you can also add some crafty neurons in the neural network or modify this model so that it can respond to a specific input, the inference evaluation. The left-hand side, the blue part, shows the perspective from a defender side. So you can prevent poison detection, poison attack by poison detection. And you can also detect whether there's perturbations or malicious noise in the input by evasion detection. And you can also prevent the model extraction by using certification and verification. The adversarial training helps us to find the malicious structure in this model such that it could prevent from being attacked by backdoor attack. So this image shows the structure of ART, the Adversarial Robustness Toolbox. It contains several modules. This one is the attacks modules. It contains 4 attacks. The 4 categories we discussed just now: the evasion attack, poisoning attack, extraction, and the backdoor attack, which is also called inference. And this part is the defenses module. We could use this module to implement the defense methods. And this one is the estimators. So it's a little bit abstract to see the estimators. So we will take a look at the examples in the following sessions. So that's one is the evaluation. We use this module to evaluate whether this model is robust enough to against adversarial attack. And that one is metric and the pre-processing. So I did not use this modules yet. So we will mainly focus on the first 3 modules in this tutorial. Now I will briefly go through the installation part so that you can install ART Toolbox after this workshop on your own. And then after installation, I will introduce the folder structure of ART. And I want to highlight there are 3 main folders that you might want to take a look at. So now we are on the GitHub page. So to install it, you click installation. And then it will redirect to another page contains how can we install it. So there are several ways. The first one is installation use with PIP. You will first need to install PIP. And then you use this command to install it. And I want to highlight this command because it supports many learning frameworks. We have to use the version of the framework that matches the Adversarial Robustness Toolbox. So to make it consistent, I suggest that you firstly create a virtual environment such that the versions of the learning framework you will install is not conflicts with current one. And then you use this command. PIP install Adversarial Robustness Toolbox. And then you replace this whole trunk. Include the square bracket with the framework you want to use. For example, if I want to use TensorFlow, I replace that part into this one. If I want to use PyTorch, I replace this part with PyTorch. And then you can also install it manually. You first redirect to the directory you want to install it. And then you use this command. But you have to install Git first before you use this command. So if you have any question on installing it, you can send me some emails. I can check whether I can help you. Okay, so that's the installation part. Now let's take a look at the code structure and the 3 main folders I want to highlight. The first one is ART. So this one is simply the source code of the toolbox of the library. So here are the source codes of attacks. If I want to take a look at the evasion attack adversarial patch, you can open it. So it contains source code of this method, adversarial patch. Sometimes you have to take a look at the source code to have better understanding. But most of the time, you can simply use this documentation. Like if I want to use adversarial patch attack, I click here. Here is the documentation of that. Like you will know what are the main methods you can use. Like the apply patch and generate. You can read how many parameters you need to input, and what are the one that you can change to satisfy your requirements. The other folder is the examples. So this one is really important because you can use various framework to use this library, but you have to know how can we use that. So this is a code contains an example of applying ART on TensorFlow framework. And there are also other frameworks like PyTorch. It will tell you how to apply ART in such framework. So it's really useful. And later I will get you through line by line of this Python file. I have copied it in a collab, and I will share with you how it works and line by line to interpret it. Another folder is the notebooks folder. So this one is also quite useful. It contains examples of a specific methods. For example, if I want to apply adversarial patch, so here are the examples of adversarial patch. There are two versions. It depends on your version of TensorFlow. So this is an example. And I had copied it in the collab, and we will take a look together later. Now let's going to dive deeper into how to use an ART library. So the first code I want to introduce is a hello world in Adversarial Attack. Why we call it hello world? That's because that's the most basic attack in the AI security. And we also did a small quiz on that, the FGSM from Evasion attack category. So we want to take a look together. How can it be achieved using ART? So the full name is fast gradient sign method. And if you want to take a look at the research paper that proposed such method, the name is here, explaining and harnessing adversarial examples by Goodfellow et al. Now let's dive deeper into the code of FGSM. I will send this notebooks after this workshop so that you can try on your own. I will not run it now because it takes a lot of time. So let's directly take a look at the results, and I will explain to you line by line. So this line is simply the installation of ART. You can use this command. If you are in Jupyter Notebook, here I use Colab Notebook. You put this operator here, and then you can run the command on the code block. So here we import all the libraries are necessary for this work. We are doing FGSM Evasion Attack. So the first part is TensorFlow libraries. Why we are going to use that? It's because that we need to use TensorFlow to define the model first, and then it will connect with the ART library. So please just load the libraries you use as what you will do normally. And that parts are modules from ART, and I will come back to explain to you when we encounter them in the code. So this step is very basic one. Just load the MNIST dataset. I believe most of you had do that many times. And this block simply create the TensorFlow model that is a target. Like this is a model we are going to attack. So in this block, please define your model using TensorFlow first. And then please take a look at this step. So this one is very important. This is different from what we will do in TensorFlow frameworks. This line introduces the Keras classifier. We load that from ART estimator classification. The meaning of it is that we want to evaluate the attack performance on this classifier. And it conducts classification task, so it's loaded from the classification part. We load the model we defined just now using the TensorFlow library to the Keras classifier. And then we train the ART classifier. Please note that we train the classifier after we create the ART classifier. So it's not on TensorFlow, rather it's on the ART classifier. We set the batch size and the epochs as normal. To know what is the attack performance, we need to know the classification results without any perturbation, right? Before we apply attack. So we need to see the classification results before we apply the attack. So in this part, we use predict method to find the prediction results before attack. The results is 97.95%. So it's quite high and just is as expected. So in this part, I draw the image before attack. So that is the image without any perturbation or noise. And the results is quite high, which is 97.95%. In this step, I'm going to apply FGSM. So that's also very important. I use fast gradient sign method, but the name is called fast gradient method. I load this method from ART Attacks Evasion module. And then I set the estimator as an ART classifier I defined just now, and I set epsilon as 0.2. So the epsilon here is just the, have you remembered the 0.007 before the perturbations? We times this constant, we multiply this constant with the sign of the gradient of cost function. So epsilon is actually that constant. To show you what's the effect of this constant, I create two adversarial samples, one with epsilon of 0.2 and the other is a epsilon of 0.8. And then later we will see the difference of these two. Here I create an attack object using fast gradient method. And then I use generate methods x equals to original image and then generated adversarial test dataset. So that dataset contains test images with perturbations. And this one is similar, but the epsilon is different. It's larger, it's 0.8. Now let's see the image after applying FGSM. So that's the image with epsilon of 0.2. As you can see, it's quite different from the previous one, right? The perturbation is very obvious, it's 0.2. However, let's compare to the adversarial test image with epsilon of 0.8. We can see that by our own eyes, right? So it's quite detectable. The perturbation is obviously much significant compared to the previous one. But what will be the attack performance? So I believe you have some answer in your own mind, but let's take a look. So that one, we get the predictions results of our ART classifier on adversarial test dataset with an epsilon of 0.2. So this line shows the accuracy on adversarial test examples. With epsilon 0.2, it is 28.27. So it's already quite low, right, compared to the original 97%. But how about the one with epsilon of 0.8? The classification results drops even much lower. It becomes 12.47%. So compared to the one with lower epsilon, the attack performance becomes much better. So it also explains the constants before the sign, before the perturbations. So I believe now you have a basic understanding of how to apply FGSM and also the constant effects on the attack results. Now let's take a look at a more advanced attack, which is adversarial patch attack. So let's go back to our slide first. So it's also a kind of evasion attack, but different from previous one, which is some noise. This one, we add an adversarial patch in the image. So it could be generated on digital world through optimization, just what I had discussed before, by increasing the cost function of the targeted model. It can be printed and added in any stand to attack in real life. For example, if I want to attack the object detection system, I can use such adversarial attack. And this image gives you a very intuitive example. The people with this patch will not be detected, but people without, it will be detected. So now let's take a look at how we can do that in ART. So that's the code of adversarial patch. So similar to previous one, we load all of the libraries we use in the TensorFlow framework to create a model. And then when we load the estimators.classification, the ART classifier. After that, we load the adversarial patch attack from Evasion module. So these are the settings. So this numbers decides what are the results of our adversarial patch. So please take a note at this one, the target name. The meaning of the target name is that we want the classifier classify all of the image, no matter what class is it, as a target, as a toaster. Yeah, that's our target. So we set it as toaster. You can change to everything, every other thing that you want the classify be misclassified with. So that's the shape of image. So here are the settings you can explore on your own. So this is the number of classes in this data set. So these are some settings to define a model. So it seems like quite complicated, but this code block simply assign ResNet 50 to the model. We use the very common used model ResNet 50 in this case. And then after that, we load the model we defined just now into TensorFlow classifier. And then we want to estimate the power of adversarial patch on this classifier. So here is a pre-processing of training images. Sometimes we need to change the dimension of images or add some modification. In this part we change RGB to BGR, so it's not so important. Simply pre-processing or change the format. So this part is really important. That's the core functions of this code. I use adversarial patch method from the ART Attacks Evasion module. I input the classifier, the ART classifier I defined just now, the TFC. And then I set the other factors of this function. I want to highlight what is rotation max. Sometimes we want the adversarial patch more robust. The meaning is that there must be some transformations like rotation or changing of brightness or contrast in real life. When we print those adversarial patch and attach it to a human, there will be some transformations. So during the training stage, I add some random transformations that in the range of rotation max to make it more robust, so that when there is a rotation, when it is used in real life, it can also have a good attack performance. So, and also that's the learning rate, max iteration, and batch size is similar to what we will do in training a model. So in this part, we want the classifier misclassify any class as targeted class toaster in this case. So we want to convert the text label toaster into an array, into a tensor that could indicate the target label toaster. So that is actually similar to what we have done in TensorFlow. So this is an object I created to generate adversarial patch. And then I apply generate methods to this object. I set X, the input as a training at the images. That's actually the set of targeted images that we want to attack. And then that's the targeted label. We set it as toaster. It's simply the tensor represents toaster label. We got it from this line and then we put it here. It will generate two variables. The first one is patch. A patch is actually this one, this circle stuff with many colors. And this one is patch mask. I will introduce in the following stage what is patch mask. You can see actually this adversarial patch looks very weird. During the optimization stage, like the generation stage, actually we are optimizing the value of each pixel. We all know that RGB image, the values are from 0 to 255. There are three values. They represent red, blue, and green separately. So in the optimization stage, we are changing the value of the pixel. So here we apply the patch we get into the images. Then we get a patched image. So that's also the method I got from the library. So in this part, we are going to see the results of patched image. What will be the classification results of the detector, ART detector, when the image is patched with the optimized adversarial patch? So here is a patched image. Now I'm going to talk a little bit more about the patch mask, which is shown here. A patch mask is actually indicates the position of this patch. So outside this patch, the patch mask will be 0, 0, 0, 0. So this image is composed of 0 pixels. So it's actually 225 times 225. So there are such amount of pixels. And if we want to indicate the position of it, we can set the positions of, we can set the value of the patch mask. If the patch is not at this position, I set it as 0. If the patch is in this position, I set it as 1. So besides the circle area, all the other parts will be 0. Only this part will be 1. So patch mask is actually a tensor that indicates the position of this adversarial patch in the image. So after explaining the adversarial, the patch mask, let's take a look at the prediction results. So here are the predictions results of the TensorFlow classifier. The confidence of toaster is highest, which is 38.39. Actually, it's a bagel, right? However, it's not the highest. So actually, this classifier is mislead and is fooled by our adversarial patch. It misclassifies it as a toaster. Let's see other example. So actually, it's a dog, but after we apply this toaster, after we apply this adversarial patch, it becomes a toaster with the highest accuracy of 24.77. So similar for this image, it misclassified the original class as a toaster. So that's a powerful implementation of adversarial patch. So here comes to the end of our workshop. I had finished the demonstration of the ART library. So here comes to the end. So could you please scan the QR code and send some feedbacks? And at the same time, if you have some questions, please come up it. I will try my best to answer you. You can either open your mic or type it in the chat. Yeah, no problem. No problem. After you submit your feedback form, so you can leave this Zoom meeting and welcome all of the feedbacks and any questions. If so, you can send it in my email, and I will send you the collab notebooks and this slide through email. Or it's not a series of lecture, there's only one lecture. No problem. If you want to learn it on your own, I recommend there are some tutorial videos provided by IBM. It's about ART, and they also cover the AI security part. So it includes both concepts and hands-on exercise, so you can watch it on your own. Oh, I believe there is a cybersecurity lab, but I'm not sure which institutions it belongs to. You can search on Google. Also, here is the link I mentioned for the FBM courses. Oh, no, I'm not. I'm actually sharing what I did for my internship last year. Yeah. But I know that there is a security lab. Maybe I can search for you. Yeah, no worries. Yeah, there is actually a cybersecurity research center at NTU. You can take a look.